Okay, so we're going to move on and we're going to specifically be looking at residuals today. We've seen residuals, or at least we looked at how they can be used to generate the line of best fit. But how about just calculating the actual residual itself? So residuals can be used to check the reasonableness of a linear fit. So how convinced are we that a linear fit is appropriate for the data set we're working with? It can also be used to identify any possible outliers. So checking the size of the residual is an indicator of whether or not a data value might be an outlier. Now this is something you've probably been doing intuitively, but now formally we'll be able to point out the outlier. So just a little bit of new notation. Residuals, we usually use the letter epsilon, and this is a lowercase epsilon here. So in general, if we have a regression line for a dataset, every residual is found by calculating the distance between its y value and the y value that will be generated by the equation. Something to bear in mind is that the sum of all residuals will be 0. So let's have a look at this. The regression line of y on x is given by this particular function. So this is the data set that we're working with. This is the regression line. How would we find residuals? For each of these values, I'm going to go ahead and I'm going to subtract the y value from the data set away from the y value the function, the equation would lead me to get. The difference between them is the residual. So I can set this out in a table, a column for the x values, and a column for the y values, and a column for the y values I would generate from the regression line. Finally, a column for the residuals. So the difference between 1.2 and 1 is 0.2. The y from my dataset is larger than the y value that the regression line would generate. 1.7 minus 1.8. This time round, my value is lower than what the function, the equation, would have generated. We continue to get residuals of negative 0.3, 0.2, and 0. Once again, the residuals would all add up to 0. So we could try to just add these together and we realize we get a sum of 0. So let's not forget that actually in generating the regression equation, we made use of the residuals. The equation itself is the equation that minimizes the square of the residuals. So inherently, the residual summing to 0 is built into the regression line equation in the first place. Okay, so if I have all of these, we can actually show these on a residual plot. And here I'm just actually plotting the size of the residuals. What you're seeing here is just how far away each of these points are from the regression line. So the first point is 0.2 in distance, the second point is 0.1. We can tell which points are closest to the regression line and which points are furthest. If we were asked to make an assumption or to predict which of these would be an outlier, it would be the value which has the largest residual, the largest magnitude of the residual. In this case, it would be 4. The point 4, 3.1 has a residual of size 0.3. It's the largest residual. It would be the point that's the furthest away from the regression line. And we can actually just see what this would have looked like on the original scatter diagram in the first place. So there's the points, there's the regression line, and here's the residuals. And we can see from this already that that point, 4, 3.1, it is the furthest away from the line. All of the others are quite close or exactly on the line. That point, if any of them, would be the outlier. Okay, so when we're looking at our residual plots, we actually we don't want to be able to see any pattern in the way the residuals fall. We almost want it to seem quite random. Some of them are above, some of them are below. We don't want any trend or pattern to them. If we do spot a trend or a pattern to the residuals as we've plotted them, it's actually an indicator that the linear model, the regression line that we've chosen to use, is not actually appropriate for the data that we're working with. Here's an example of 3 different residual plots that actually have some sort of pattern to them. One looks to have a positive gradient, one seems to have a negative gradient, and one actually seems to be a quadratic curve. All of these are indicators that our linear regression model is not appropriate. In the first instance, if the residuals have this pattern, it means on the scatter graph, the original points, the plots, were quite low below the regression line. Soon they started to be close to the regression line, and soon they were quite far above the regression line. It actually looks like a different linear regression line might be a better fit, or maybe it's not even a linear model at all. Similar to the second one, here it looked like there was negative gradient in the residual plots. That means that the initial values were above the regression line. They had positive residuals. The positive residuals were getting smaller as we went along until we actually had 0 residual, or we started to have negative residuals, and those negatives were getting larger and larger as we went along. And finally, this one where the residual plot looks like a quadratic means initial values were large positive residuals, smaller positive residuals, negative residuals, and then we go back to small positives and off to large positives. This doesn't look linear at all. This looks like a curve of best fit would work a lot better. So, any pattern to the residuals is an indicator that our linear regression model may not be appropriate. Okay, let's throw in a little bit of problem solving with calculating these residuals. So here we've been given some data. We know all of the temperatures, but not all of the sales. One of them is in terms of P. And we've been asked to try and find out what P is. Well, let's go ahead and fill in our table as usual. So I've got my T values and my S values, and here I'm calculating the output I would have got if I substituted into the function. Now, we need to find the difference between each of these and the actual data point value that we found. This generates some residuals for us: negative 0.3855, positive 0.6452, and then we continue with some more negatives and positives, and this term in terms of P. P minus 20.2627 is the residual for this fourth point. Well, how are we going to find P? We know that all of the residuals should sum to 0. If we add together the epsilon column, it should equal 0. From there, we get P minus 20.9977 equals 0. Rearrange to get P equals 20.9977, which rounds to 21. Next, we're asked to consider and comment on whether the linear regression is suitable. So I'm looking at the residuals, and they do seem to be random, as in I've got some negatives and positives all mixed up with each other. So no clear pattern to the residuals we're working on. So I'll conclude that since the residuals seem to be randomly distributed about 0, a linear regression model is suitable. And we'll just finish up here with the residual sum of squares. Now this is a measure, a numerical measure, that helps us to decide just how close, it indicates just how close the points were to the regression line. If all of the points were exactly on the regression line, the residual sum of squares would be 0. So the smaller it is, the closer to that regression line. We can calculate the residual sum of squares, the RSS, by using this formula. There is an alternate version here, but it uses R, which we haven't yet worked with, or do you know how to calculate? So I will revisit this after we've looked at R, the correlation coefficient, which we'll be doing in the next chapter. Okay, so let's use that formula to find the residual sum of squares. Here we have a data set and we have some summary statistics. We've been asked to calculate RSS. I just need to calculate my summary statistics and substitute them into the formula. So since you're quite confident with these, we've looked at them extensively in the previous exercise, I'm just going to whiz through. So the S of XX, if we substitute our values in, we get 12.352. Similarly for the S of YY, the sum of y squared minus the sum of y squared over n, substitute in and we get 3.668. For S of XY, once we substitute our values, we get 6.704. Okay, now that I have these three, they can be substituted into the RSS formula. Substituting in, we get an RSS of 0.0294. So very small, but is it small enough? When we compare it, August has a lower value for the RSS than December does. So the RSS indicates that August's values are more likely to have a linear fit.